All right, hello and welcome to Exponential Growth and Decay. So this is going to be a short video that covers one example of exponential growth and one example of exponential decay. Here's your socks here. There you go. All right, so example number one. All right, so we've got a population of bacteria on a piece of cheese is given by the formula P is equal to 500 e to the power of 2t. Show that P satisfies the differential equation dp dt is equal to 2p. So firstly, what is a differential equation? Right, it's an equation that has, well, a combination of the derivative term, this is the dp dt, and the actual original function, which in this case is P. All right, so we've been given what P is. We just need to show that it satisfies this differential equation here. Nice and simple. We already know what P is. Now we just need to work out what dp dt is. So take the equation given. Let's differentiate. So dp dt, or, if you wanted P dash, would be equal to, right? How do we differentiate our exponentials? Bring power down the front. Sorry, I should say you bring the derivative of what's at the top, comes down the front, and then the exponential remain unchanged. And by doing this, two lots of 500. Okay, this is us differentiating. So now that we know what dp dt is, we can then sub these things into our differential just to see that it works, right? Well, we know what dp dt is. It's 1000 2t. So our left-hand side is just this. The right-hand side is 2p, which funnily enough just ends up being the exact same thing. Okay, so here we can see, therefore, the left-hand side is equal to the right-hand side. In other words, the equation does satisfy the differential equation. All right, part B. All right, find P, the population, and P dash, the rate of the population when T is equal to 0. Right, this is initially, right? When T is equal to 0, it means right at the start, what are these things? All right, so the population, as we know, is given by this. We're going to let t equal 0. And so this initial population is going to be 500 e to the power of 0. Anything to the power of 0 is 1, so you just end up with 500 times 1. Okay, so in this case, the initial population of bacteria is 500. What would P dash be? Or dp dt, right? What that stands for is how much is the population changing? Well, dp dt is equal to, we found this formula in part A, it's 1000 e to the 2t. We're trying to find the initial situation, in other words, when t is equal to 0. So yeah, you end up with, ultimately 1000. So what this refers to as P is equal to 500. That means initially the bacteria, there was 500 different bacteria cells on this cheese. And P dash being equal to 1000, what this stands for is initially the bacteria was increasing, right? So initially there's so we started with 500 bacteria, but it was increasing at a rate of 1000. And we actually don't even know what the units are for time. I'm going to assume, days, hours, minutes, weeks, it could be whatever. I'm going to just assume for this question that it's days. So it's increasing at 1000 per day, at least initially. All right, part C. Hey, Angus. Find T when P is equal to 1 million. So in this case, we started with population of 500. Now we're trying to find out, well, what will t be, right? How long will it take for the population to reach 1 million? Well, our population is given by 500, e to the 2t. We're going to let p equal 1 million. And so we end up with 500 e to the 2t is equal to 1 million. And then just go ahead and solve this equation, like you normally would. Rocking out without a calculator for whatever reason. I believe it's 2000. And okay, from this point, how do you get t by itself, right? What we're going to do is I'm going to log both sides. I'm actually going to use log to the base e. So bringing the 2t down the front, this will end up just becoming 2t. Why? Because log to the base e of e is equal to 1, right? And over here you've got log to the base e, or you might see the shortcut on your calculator just written as ln 2000. So in other words, t is going to be log to the base e, or ln 2000, all divided by 2. So you type that in your calculator, press equals, probably round it to like 3 decimal places or something like that. Or you can keep it in exact form. So either would be totally fine. I'm actually going to just bring up, I'm not even sure if the calculator I've got has logs in it. Hey, mate. Oh, thank you. Oh, it does. Okay, and then divide that by 2. Okay, so we end up getting 3.8, right? Whether it's days, weeks, it just depends on what the units of time are for the particular question. All right, I've rounded to 1 decimal place here. Okay, and final part, find t when dp dt is equal to 4,000. So again, look at what your formula is. I believe dp dt was 1,000 e to the 2t, and we're going to let dp dt equal 4,000. So in other words, we end up with the equation this, and again, you just solve it, like you always do. Again, log in both sides to the base, log to the base e, right? Or in other words, ln 4, and so t would end up being ln 4 all over 2 as an exact value, or if you wanted to round it, you could do that too. All right, so that's an example of exponential growth. Now let's look at the situation. Oh, and by the way, what does exponential growth look like? You've probably seen it before, right? Exponential growth. In this case, not that we need to for this question, but, bacteria started off with like 500. There's 500 different bacteria cells on the piece of cheese. And it was actually, growing quite rapidly. And it will continue to grow faster and faster. Let's be perfectly honest. We went from 500 bacteria up to 1 million in less than 4, days or weeks, whatever that happens to be, right? So there's quite rapid growth. So anyway, that's an example of exponential growth. Now let's look at exponential decay. These are the situations where, something would start off, with some sort of initial thing, and it would go down rapidly and then sort of start slowing down. This is exponential decay. Now, here we've got a radioactive substance of mass m that is decaying such that dm dt is equal to minus km. We want to show that this formula here, the mass of the radioactive substance is equal to MO e to the minus KT satisfies the differential equation. They're referring to, this is our differential equation, right? Okay, so we need to show that this is the correct formula for this particular situation, that it satisfies the differential equation. Well, we know what M is. Let's work out what the derivative is. So remember, when differentiating exponentials, you differentiate the top term. So, you know, the derivative of minus kt. Differentiate what's at the top, you just get minus k. So the derivative comes down the front and it's multiplied by the rest of it, unchanged. Which, funnily enough, what I'll do is, instead of doing it the way I did last time, you know, I'll do it the way, you know, I would have personally done it myself. Check out this. What do we have right here? M to the 0 of e to the minus kt. That actually happens to be, check it out, M. So we can replace that with M. And here you see, we've just shown that dm dt is actually equal to minus km, which was the differential equation. So that's another way we could have done part A, just like we did in the first one. We could have done the exact same thing over here. It would have been right here, we would have made the substitution for, in that case, P. But anyway, either way works fine. Whatever comes naturally to you is definitely the best way to do it. All right, given an initial mass of 150, in this case I'm going to assume grams, find MO. So we want to find the initial mass, right? Initial means we're referring to, we're going to let T equal 0. All right, so we have this formula for the mass, which is e to the minus kt. By the way, why is there a minus up the top? It's because it's decaying. This radioactive substance is losing mass as, you know, these particles are being converted to radiation. So the mass is actually going to be dropping, which is different to the population of bacteria on the cheese from the previous example. That's why we've got the negative here. Anyway, we're going to let t equal 0, and we know when t is equal to 0, initially, the mass was 150, right? The initial mass was 150. So let's make these substitutions. 150 is equal to MO e to the minus, well, in this case, 0 minus k times 0. All right. And we know e to the 0 is equal to 1. Therefore, we were asked to find MO. It's 150. So now we've got this situation where the mass of this radioactive substance, now we know what MO is. It's actually 150 e to the minus kt. We've now worked out what that MO is. All right, on to part C. If the substance has a half-life of 10 days, find the value of K. All right, so they've sort of brought in a physics term here. Half-life means that it's the time taken for a substance's mass to reduce to half, and it's 10 days. So in other words, what this tells us is a half-life of 10 days is when T is equal to 10, the mass would be equal to, right, we're talking half the initial amount. So we went from 150, 10 days later, that substance will now only weigh 75 grams, right? Because, you know, it's been decaying. All right, so this is what it means when it says half-life. All right, and we want to find the value of K. So what do we have so far? Okay, the mass is given by 150 e to the minus kt. And we've been told that, I'm going to write it this way, that when T is 10, so we end up with a minus 10K there, we end up with a mass of 75. Okay, so here we go. We've got our equation set up. We now just need to solve it to find the value of K. This is going to be pretty simple because we know how to log both sides. Divide both sides by the 150. You end up with a half here. Not surprising, it was a half-life. And then, log both sides. So log to the base E. And you end up with ln a half. For those that are thinking ahead, you're like, well, hey, if we do this, aren't we going to end up with... Sorry, I just wish that was neater. All right, so we're going to divide by the -10. And you may be thinking, oh, we're going to end up with a negative K, but we already had a negative at the top in front of the K, so the whole thing becomes positive. So a radioactive substance is actually increasing in weight. Not the case. Fortunately, we're saved by the fact that the log of a half is a negative itself. So this all works out great. K is going to be, here, I'll write it as a fraction. A -1/10 log to the half, right? Or you could have put it all over 10. I just thought maybe it looks a little bit neater this way. I'm not 100% sure, to be honest. Anyway, that's the value of K. That's what we needed to do for part C. This implies, now, just before I move on, that the mass of this particle is going to be given by, check it out, is 150, right? We discovered that in part B. E to the minus, and we now know what K is. It's a -1, so it ends up being a positive 1/10 log half times T. Hang on, I'll put the T right there. Again, got issues with neatness. So that's a E to the T over 10 log to the half. This formula here, now that we've found MO, we've found K, we've now got the formula that's going to give us the mass. And we want to find the substance's rate of decay after 30 days. They actually don't want us to find M. They want us to find dm dt, the rate at which the particle is decaying. So let's check it out. Bam, right up here, right? The rate is dm dt is equal to minus km. Or we could have used the modified formula, but this will work fine. So we want to find the rate of decay after 30 days. We know what K is. Right, K is a -1/10, so this ends up being a positive 1/10 ln a half times the mass. So we just need to find the mass of the substance after 30 days. Fortunately, we've got ourselves a pretty good formula for that. Let T equal 30, and ultimately you end up with 30 over 10. So 3. All right. So you type this into your calculator. You get your mass of the particle after 30 days. And then you can then sub it in here to find the rate at which the particle's decaying after the 30 days. All right, we'll leave it there. Best of luck. If you have any questions or anything, just leave a comment either on YouTube or Canvas. And I'll see you in the next one. All right, thank you.